Welcome back to session 14. This is part 2, and we're going to focus more on the shear stress in beams. So to kind of get a feel for what is happening with internal shear stresses in a solid beam, let's take a look at kind of breaking a beam into a series of thin laminates. So here we have our beam, and it's simply supported on two ends with a force acting in the middle, and we expect it to bend as we see here. So there's going to be some internal bending moment, there's going to be some internal bending stresses, which we've covered previously. Now, if we take that same geometry and we think about this beam being composed of a series of stacked pieces of wood, like what we see here, okay? And we look at the deformation, we see something very similar. Now, in this case, let's just assume that all these laminates are perfectly glued to each other, and the response is actually identical to what we had in the solid case, okay? So now our objective is to look at what is happening along these interfaces, okay, that we see here. And we get a sense that if we were to not have these pieces glued to each other, okay, so if we had sliding laminates, then we would think, okay, there's less resistance to the bending, okay, and what is happening at these interfaces that is causing this resistance to the bending? And it's shear stress. It's stress acting along these surfaces, okay, which is what a shear stress does. It acts tangent, and it is keeping these sheets from sliding against each other. Now, in a few minutes, we'll also get into the derivation for what the magnitude of the shear stress is. But for now, just think about there being a shear stress acting along these interfaces when we apply a force in the middle, or when we apply a bending moment, or when there's an internal shear force across this beam. And another thing to keep in mind that we'll derive, but it's not necessarily obvious right now, is that this shear force, or this shear stress, this transverse shear stress, okay, which is acting along the longitudinal direction, okay, or orthogonal to the direction of the load, the P, okay, or the vertical direction, this transverse shear stress actually gets smaller as we get farther from the neutral axis. So the transverse shear stress is typically the largest at the neutral axis, and it decreases as you go to either the top or the bottom of the beam. Now, let's just go back and think about what would happen if these laminates were able to slide against each other, or these sheets were able to slide against each other. You'd see more bending, okay, for a given amount of force, and you would not see as much shear stress inside, okay, because these sheets would be able to slide against each other. So to answer this initial question, how do the internal shear stresses compare in a solid system versus one with sliding laminates? Well, the shear stresses are going to be higher, okay? Even though we can't see the sliding, the shear stresses are going to be higher when you have this solid structure versus you have a set of laminates that can slide against each other. And I guess this is not everything in this course is about springs, okay? But there can be spring designs or leaf springs or different designs where you might actually want to have a little bit of sliding, okay, between the laminates, and you could control the spring constant, essentially, the force versus deflection. But we haven't gotten to deflection yet of beams. And then one kind of final little kind of tidbit of for your good to know information, and actually maybe it's beyond for your good to know file, is that since the maximum shear stress is at the neutral axis, it is possible that there can be failure, okay, closer to that neutral axis. Now, I do not know what this piece of fiberboard experienced when it failed, and we can see that there's tearing here and tearing there, and so there was likely a lot of bending stress, maybe, I don't know exactly what's happening near the surfaces, the top or bottom surfaces, which is what we expect, but there may have also been some internal shear stress near the neutral axis, and that's what you see here with this kind of torn region in the middle. I'm just guessing, but engineers essentially often become detectives to try to figure out why something failed after it failed. And so having a sense of what the internal shear stresses might have been, what the bending stresses might have been, gives us an indication, well, did it fail at the outside? That would be kind of due to bending stresses, or did it fail near the neutral axis, which would be indicative of high shear stress. Let's now look at shear force along a beam and think about how we might envision this system being dependent on the different geometric parameters that we have here. So first thing we do, right, is we look at the equilibrium, and we're going to say, okay, we've done this before. We know that MR is equal to FL. We know that R is equal to F, and we can look at the boundary condition at the left, and we can go ahead and say, okay, the internal force is, or the internal shear force is going to be equal to F, the boundary condition at the right. We're going fast. We've done this before, right? And we know that we have V is equal to F. So the internal shear force can be thought of as just being equal to F. And that's a constant along this beam. So if we think about the shear force, okay, acting here on a face or on a slice along the beam, we can also associate it with acting over an area and think about what the shear stress would be on these individual elements, DAs, on this face. And that is what we will prescribe to be tau. And we can say that tau dA is going to be a little bit of a piece, a dV, of the shear force, V, okay? And you might have caught this a second ago. It's not the same necessarily across that whole face. And we might also be wondering, okay, this shear stress is acting on the face that's been cut. This is orthogonal to that transverse shear stress that we said was acting along the beam. Well, we're going to get there and discuss that in just a second. But first, what we can say is that there's an equivalent average shear stress related to the shear force and the area. Okay? And this is commonly written as tau av equals V over A. And this is, you're thinking, we just did this. What does this look like? This looks like the single shear case, right? Where we just discussed where if I shorten the length quite a bit, I get a situation where I have very little bending moment, and it's dominated by the shear force. So one thing that we do keep track of, and we use this average shear stress as an important quantity when we're looking at shear in a beam, okay? And when we come up relationships for what the maximum shear stress is across a face of a beam that we've cut, and thus the maximum transverse shear stress being at the longitudinal, or the in the longitudinal direction, and at the neutral axis, we often come up with relationships that are related to this average shear stress. So the average shear stress is just an average, and it is not the same at the neutral axis, and it gets smaller as we go up or down, right? This is what we were discussing a second ago, or a few minutes ago, when we were looking at the transverse shear stress along the beam. And if we take a little element, okay, from this face, so now this face right here is this face right here, and then this element goes into the material, okay, so that's going back. So this is a 3D element. If we were only to have this one shear stress, which is going to create a force, right? This is like a dA, this is a shear stress, there's some little dV acting on this face. This element would spin, right? We wouldn't be able to preserve equilibrium. So what happens? We have to have a corresponding shear stress on other surfaces of this element. And maybe the most obvious one is going to be on the top. And this shear stress on the top, right, along the direction of the beam, the longitudinal direction, this is what we consider to be the, I guess, abstracted transverse shear stress, right? This is the one that's orthogonal to the internal shear force. This is the one that's on the longitudinal axis. This is the transverse shear stress. But this is also transverse shear stress because this is equivalent, okay, to this one. But this is in the direction that we've been discussing previously. If we rotate now this element and take a 2D perspective, what else has to be true for equilibrium to hold? Well, on this bottom surface, there needs to be a corresponding shear stress to make sure that this element does not rotate and that the element also does not translate, right? Because if I just had these two up here, then it would kind of want to go down to the left, but there have to be corresponding shear stresses that we see here, right? And if you think back to how we defined shear stress a while ago in previous sessions, we don't typically care as much about direction with shear stress as, say, when something's in compression or tension, but it is important to note that it does have a positive and negative convention that we do follow. And so this would actually be negative, given what we have here. If the two arrows come up to the top right corner, that's positive. If they come down and away, that's negative. So we've now kind of qualitatively discussed transverse shear stress, and then we've gotten a little bit closer to a quantity with the average shear stress. It's now time to derive the localized shear stress. So let's start with this beam that we have here, in a face with a shear force and a distribution of shear stresses. We take a slice of this beam, and it has some width dx. Okay, so we're going to say that this quantity right here, that's the dx. We also recognize that our beam has a neutral axis. So if we kind of draw it across here, we see it as shown. Now, we're going to take this element and we're going to rotate it and look at a side profile like we see here. So this element has been rotated. Now this dx that was kind of going into the page a little bit is now looked at as a profile on the side. And what we have here are a neutral axis and a bunch of bending stresses. And we're thinking, what in the world is going on here? Well, we know that I mean, this is actually, we derived this previously. If we have bending stresses, right, we can think of, if we have a bending moment, we can think of the bending stresses, okay, given by this shear formula, or the flexure formula, sorry, not the shear formula. That's what we're trying to derive. So we still haven't really figured out where the shear stress is on this slice, on this cut. So what are we going to do? Well, let's go a little bit further and break it down into looking at what is happening on this profile of a slice. Okay, so here this is the same profile. This is just saying, hey, there's transverse shear stress, and this is the slice that we were cutting. Let's look at what happens if we cut the slice. What do I mean? Look at this. We have now this profile, and we can deselect or cover up a bottom portion, as we see here. There's still a neutral axis going through this location, and it's still acting, and I can define, I gotta be careful what I say. It's still there. The neutral axis is still there, and we're going to define a new parameter called y prime, which describes the distance from this neutral axis up to some horizontal line. Okay, so we've actually, what are we doing? We've cut this portion and we're leaving this portion, and we're trying to get a shear stress, a transverse shear stress. Well, look, this element still has these quantities acting on it. Okay, the bending stresses, and we're going to define some term for A prime in a minute. But the key thing is for this to be in equilibrium, okay, with this m and this m plus dm, and we're saying, hey, maybe this sigma prime is different than sigma. And if that's the case, what's keeping this element from accelerating left or right? And that is where the shear stress comes in. So as we are looking at this system and we don't want it to accelerate, we want it to be in static equilibrium. If there's a little bit higher summation of force on this side, on this A prime area, we can compensate it. We can compensate for it by having a shear stress acting over an area dictated by the width of this section and the width or the distance into the board as well. Okay, so there are kind of two widths. The width that we typically think of with a beam is going to be this width. Okay, we typically call that a B. All right, so you would have something like a B or a T. Okay, in transverse shear stress we actually use T. Okay, often, but that tau times that width times dx is going to be a force that can act against this sigma prime, acting over the width into this system and this height of this selected element, okay, or the selected portion, better said, of the beam. Okay, so now we've done equilibrium. We have to do some math. Okay, and what is the math going to involve? The math is going to involve taking this nice little slice that we have, defining some parameters, area A prime, the Y prime. This is the same parameters that you see here. Also defining a centroid, not of the entire face, but of this area A prime, which is dictated by Y prime. What we're essentially trying to do here, and this is an important point, we're trying to figure out how the shear stress depends on its distance from the neutral axis. And what is the distance from the neutral axis? It's Y prime. So this A prime is going to change as Y prime changes. The distance to the centroid of this area is going to change as a function of Y prime. Okay? And as we do the math, it'll become more apparent. Thickness is this width, right? We describe that as B often in our problems. And this thickness, it's nice for a rectangular profile, but it can also change as a function of Y prime. So T would be equal to B, the width for a rectangular profile, but if it's not a rectangular profile, then T could change. So here comes the derivation. We're going to work on summation of forces in the x direction and making that equal to 0. And as we were saying on the previous slide, we have a shear stress, tau, acting, okay, over this dimension dx into the board, and that has some thickness t, okay? So this is a stress times an area, which is equal to a force. Similarly, we have a force due to stress, a bending stress, okay, summed over this side. We have a force due to a stress, sigma prime, on this side, acting over, they're both acting over dA primes, okay, but this is on this side and this is on this side. This one's going this way, which we'll call to be negative, right, as we're saying that to the right is positive. So what is sigma? Sigma can be related to m, okay, through the flexure formula. Okay? And so we can say that we have either a sigma equals my over I, or the sigma prime is equal to m plus dm quantity, okay, quantity m plus dm times y over I. And what we can do is a little bit of substitution, and we plug in our m or our flexure formulas, okay? We use them to substitute in for sigma. We have an m over here, we have an m over here. They're integrals over the same region with respect to the same dA prime. So that means that we can potentially subtract them and get that we are left with just a dm over I y dA prime in the integral. And we can go a little bit further and break out the quantity dm if it's not changing, and we say that we have our I. This is the same I that we had before. This is the second moment of area. This is dependent on the cross section. Okay, we have our TDX, and we have our integral a prime y dA prime, and we can rearrange things yet again, and we're like, oh, wait a second, dm dx, I've seen that before. This is 1 over it, and then this quantity here. dm dx, what is dm dx? Ta-da, finally, even though v is not drawn on this slice, v is equal to dm dx. This is kind of a cool deal, all right? Because we've been saying, look, there's a average shear stress, and that average shear stress is related to the localized shear stress. This quantity over here is something we call the first moment of area, and it's given by a big Q equal to the integral of, well, what you see there, y dA prime over a prime. And when we finally put everything together, even though this formula has been sitting here for the last few minutes, we can make a new expression for the transverse shear stress as being V, this quantity, right, times Q, this quantity, over IT. And we're going to spend a lot of time with this expression. This expression is what we term the shear formula. This Q is the first moment of area, and we're going to have a whole part of our session discussing the first moment of area. And there's also this other version of the first moment of area. And previously, a few minutes ago, I hinted at, okay, we might want to use the centroid here as a way to help us calculate out what Q is. So if we have a beam, as we see here, we might think about an X dimension and a Y dimension. And we're going to still be taking slices and still looking at an internal shear force, a bending moment. And this is just an example, okay? And actually, this is just an example too, because this is for a rectangular cross section. What I'd like to do is just rewrite the shear formula in a form that's similar to what some of the other instructors or books or online sources do. And that is in terms of the parameters that dictate what these quantities should be. So for example, sure, you just write VQ over IT on your formula sheet or on your note sheet, but it's important to remember that this internal shear force is really dependent on where it is along the beam. So that's along the X direction. Q, the first moment of area, okay, is going to be dependent on how far we are from the neutral axis. So we could say that's dependent on a Y prime quantity. I, that's the second moment of area, that's actually dependent on X, okay, so where we are along the beam. Usually our profiles are staying the same. I'm very grateful for that, okay? Usually our profiles are staying the same as we go along in X, but it's the entire cross section, okay? So you're not going up or down when you're calculating I, it's the entire cross section. T, on the other hand, the thickness across is dependent on the Y prime that's been selected, so the distance away from the neutral axis that we've selected. So I think it's important to kind of have a perspective, because when you calculate these things, there are these essentially four quantities that require, with the exception of maybe the thickness, require other calculations that then plug into the shear formula to be able to calculate the transverse shear stress. Well, we're at the end of this portion of session 14, and we have a question. All right, so this is the third question for the session. For a beam with a rectangular profile with a base B and thickness or height h, what is the transverse shear stress at the neutral axis along the beam where the internal shear force is V? Okay, so this is just to kind of get ourselves acclimated to the transverse transverse shear stress or the shear formula. And there's a hint that we've put here that Q is equal to BH squared over 8 at the neutral axis. So this quantity is often the most complicated to calculate for these problems. But we're giving you V, we're telling you what Q is with this expression, and this is at the neutral axis for a rectangular profile. You know how to calculate I for a rectangular profile, and we know what the width is here. Okay, the width is going to be the base B. So take a few minutes, run the numbers that you might be given, and calculate out what the transverse shear stress is. And I'll see you for the next portion. Thank you.